Hi, I'm Matt, and in this video we are going to go over the VSEPR theory for molecular bonding. So first, what exactly is VSEPR? Well, VSEPR stands for valence shell electron pair repulsion. So what it is that in a molecule, the atoms form particular shapes with specific bond angles to minimize the repulsion among the atoms and the lone pairs in that molecule. And the VSEPR theory predicts these shapes and angles that they form in. So when it comes to shapes, the first thing we are going to go over is the electron domain geometry. This is the general shape formed based on the amount of electron-dense areas, which would be the shape if there were no lone pairs present in the molecule. We refer to an electron-dense area as an area where there is a bond or a lone pair around the central atom. Double and triple bonds count as one singular electron-dense area, and we count the amount of electron-dense areas to determine what the electron domain geometry is. So, for our first electron domain geometry, we're looking when there's two electron-dense areas. All the lone pairs and electron-dense areas are based upon the central atom in our Lewis structure. So here, carbon is the central atom, and it has two electron-dense areas, because on both sides it has double bonds. We call this electron domain linear, and the bond angle in linear molecules is 180 degrees. An example of a linear molecule would be CO2. Next is when we have three electron-dense areas. We call this electron domain geometry trigonal planar, and the bond angle between the atoms would be an 120-degree angle. An example of this is BH3. Here, boron is the central atom, and it has three bonds, and the angle that made by the HBH is an 120-degree angle. Moving on to four electron-dense areas, the molecules are no longer flat, and we have to visualize them in 3D to think about their shape. So the triangle seen in the middle below the carbon shows that the hydrogen is coming out of the page, and the curved lines on either side of it show that those hydrogens are going into the page. So when we have four electron-dense areas, the electron domain geometry is tetrahedral, and the bond angle is 109.5 degrees, as shown between the hydrogens in CH4. Next, we have five electron-dense areas, and we call this electron domain geometry trigonal bipyramidal. And there's two bond angles here. So the bond angles between the green chlorines in the diagram are 120 degrees, kind of like trigonal planar. And then the bond angle between the blue and the green chlorines is 90 degrees. Basically, you could imagine this as a stick being placed down the middle of a trigonal planar molecule. An example of this would be PCl5. The last electron domain that we are going to talk about is octahedral. This is when there is 6 electron-dense areas, and all the atoms surrounding the central atom make a bond angle of 90 degrees with each other, as the fluorines do in SF6. Now that we've gone over electron domain geometry, we are going to move on to molecular geometry. Molecular geometry is the specific shape formed based on both the amount of electron-dense areas and lone pairs attached to a center atom. Remember, lone pairs are the pairs of electrons not used in bonding with another atom. And the angles in these atoms will be smaller than the ones we just talked about, because lone pairs have more repulsion than do just atoms. Now, the good way to think of the difference between domain geometry and molecular geometry is with ice cream. The domain geometry is the ice cream, and the molecular geometry is the specific flavor of ice cream. So now, let's move on to our first molecular shape. So the first molecular geometry that we are going to talk about is when there is 3 electron-dense areas and 1 lone pair. Since there are 3 electron-dense areas, the electron domain geometry would be trigonal planar. But this particular molecular geometry is called bent because the lone pair repels the two oxygens in O3. Now we are going to move on to molecular geometry with 4 electron-dense areas. So all of these molecules will have a tetrahedral domain geometry. Now the first shape we're going to talk about is trigonal pyramidal, which is 4 electron-dense areas with 1 lone pair. An example of this would be NH3, where that 1 lone pair repels the 3 hydrogens. The other shape when there's 4 electron-dense areas is bent. This occurs when there are 2 lone pairs. You'll realize how we already talked about bent when we talked about 3 electron-dense areas and 1 lone pair. Some of the names do overlap as the structures are similar, even though there's more electron-dense areas. So a good example of a bent molecule with 4 electron-dense areas is water, or H2O, where the 2 lone pairs repel the hydrogens. Now we are going to discuss the 3 possible molecular shapes when there are 5 electron-dense areas and some of them are lone pairs. So remember for all of these that our electron domain geometry will be trigonal bipyramidal. So, as is the case in SF4, when there is 1 lone pair, the molecule will take a seesaw or a sawhorse shape. If there are 2 lone pairs, such as in ClF3, the molecule will take a T-shape. And then lastly, if there are 3 lone pairs, as is the case in XCF2 or xenon difluoride, there will be a linear structure. Lastly, there are 4 different molecular shapes that we have to discuss when there are 6 electron-dense areas. Remember that if there are 6 electron-dense areas, that our electron domain geometry will be octahedral. The first shape is when there are 6 electron-dense areas and one of them is a lone pair. We call this shape square pyramidal, and a good example of this is BRF5. Moving on to when there's 2 lone pairs, we're going to have a square planar shape. This molecule is actually flat as the 2 lone pairs go on the top and the bottom, and an example of this is xenon tetrafluoride. For the last 2, there's no real known examples of them, except ions, if even at that, so here I just use balls to represent the particles. So, when there's 6 electron domains and 3 lone pairs, this is going to take a T-shaped, very similar to when there's 5 electron-dense areas, 2 lone pairs. And lastly, we are back to linear, if there are 6 electron-dense areas and 4 lone pairs, as to minimize repulsion, the atoms will be completely straight apart from each other. So now that we know all of the shapes, how do we actually tackle a VSEPR question? The first thing you have to do is memorize the chart. Now I know I didn't actually give a chart form here, but if you just Google VSEPR chart, you'll get millions of them that are good. And you need to not only know the shapes, but the bond angles when there are no lone pairs. And then know that when there are lone pairs, the bond angle will be less than that number. And when we're asked a question about the shape of a particular species, we need to draw the Lewis structure to determine the amount of electron-dense areas and lone pairs. And then once we know that, we can match it up to our VSEPR chart. And the last note is don't mix up electron domain geometry with molecular geometry, because if there's any lone pairs, they are not the same thing. Lastly, here are 4 practice questions to test your knowledge of VSEPR. So, question 1, what is the name of the electron domain with 4 electron-dense areas? Question 2, what is the name of the molecular geometry of a species with 6 electron-dense areas and 1 lone pair? Question 3, what is the name of the molecular geometry of a species with 5 electron-dense areas and 2 lone pairs? And lastly, what is the electron domain geometry and molecular geometry of NH3? For that one, you're going to have to first draw a Lewis structure to figure out the amount of electron-dense areas and lone pairs. In case you're not yet comfortable drawing Lewis diagrams, this is the Lewis structure for ammonia, or NH3. Use it to answer question 4. The solutions are as follows. When there are 4 electron-dense areas, the electron domain geometry is tetrahedral. For question 2, when there are 6 electron-dense areas and 1 lone pair, the shape is square pyramidal. For question 3, when there are 5 electron-dense areas and 2 lone pairs, the molecule is T-shaped. And now with question 4, you should have gotten that there are 4 electron-dense areas and 1 lone pair, meaning that the electron domain geometry is tetrahedral due to the 4 electron-dense areas, and then the molecular geometry would be trigonal pyramidal. Thank you so much for watching. If you have any questions, feel free to leave them in the comments below. Have a great day.